Hello guys, I hope you're all doing well. Welcome back to my channel, and today I'm going to show you how to make something like an autonomous car with Lego NXT motors. Now, I'm not actually going to show you how to build it because as you can see in the current model, I actually just use a bunch of random parts, but you can use all of your like Lego wheels and stuff if you don't have the tracks. But basically, the thing I'm mostly going to explain here is the code. So, as you can see here, this is what like the thing I created looks like. Over here is the power bank, which is actually giving the supply to the Raspberry Pi. And all of these wires are actually jumper wires that are connected to the Lego NXT motors and other devices. So that's one way to view it. And now I'm going to quickly move to here. This is actually our diagram I'm going to use to explain to you how we actually connected it. So first let's look at all like the materials I used. This is basically the Raspberry Pi. These are all the jumper wires. Over here are resistors, which are where I've basically connected to a voltage divider. I'll tell you why soon. This is a ultrasonic sensor. The name of it is listed on here. These are Lego NXT motors, and this is a motor driver. But as you can see, the name over here is also listed. And finally, we have the servo motor. Oh, and also this is just the power supply powering the motor driver. Because it requires 9, but we're putting a 9-volt supply because these Lego NXT motors require 9 volts. Anyway, so first let's go over to this motor driver to see how it's connected in. Okay, so over here, this side is actually our power supply. So this is the like battery supply part for the positive part, and so it's actually connected to the positive side of the battery. And this is actually the ground or the negative side. It's also connected to the battery, but it is also connected to the Raspberry Pi. Now let me zoom in over here, and as you can see, there are 6 pins we're using to communicate with the motors. The first motor is attached over here, which says output 1 and output 2, and the second one is actually attached over here, which is where it says output 3 and output 4. So over here, you can see we have 6 things: ENA, IN1, IN2, IN3, IN4, and ENB. Now don't worry about these 2 pins that are above, we're not using those. So basically the first 3 are actually used to power this motor, the one my mouse is at. And the last 3, IN3, IN4, and ENB, are actually used to control this motor. So now that we're done with that, I'm showing you another part. Oh, and by the way, I'm going to show you the wiring for this. So let's see here, right? The ENA is connected to GPIO 25. The IN1 is connected to, let me find it, GPIO 16. IN2 is connected to GPIO 19. IN3 is connected to GPIO 26. IN4 is connected to GPIO 20. And ENB is connected to GPIO 23. So now that we're done with the motor driver part, let's go focus on the sensor part. As you can see, we have 4 parts of the the sensor: VCC, trigger, echo, and ground. Remember, this is the ultrasonic sensor, so the way it actually senses if an object is in front of it is by sending ultrasonic waves. Those are waves you can't actually hear, and then once you find the object, they'll reflect back. So over here is the VCC and ground. The ground is connected to Raspberry Pi, and the VCC is connected to the 5-volt pin because that's how much power it needs. So then we have the trigger pin. What this does is actually it tells the sensor to send a signal or to send waves. Now, once this pin is high, and also for this we're using GPIO 22, it will send a signal, and then this echo pin will be high, but it won't actually be activated. It will be high for as long as the ultrasonic waves didn't come back or bounce back. So once it is, the signal becomes low, but this outputs a voltage of 5 volts, which is and the GPIO pins can only take up to 3.3 volts, so it can damage the pi. So that's why we have a voltage divider here. So basically, whenever it receives something, it will send a signal telling, "Hey, buddy, I've received something." And yeah, that's the sensor part. Now we have this servo motor. Let me zoom out so you can see it. The servo motor has 3 pins this time. One is ground, which is connected to ground. One is the 5 volt supply, which is connected to the 5 volt supply here. And one is signal, which is actually to tell it how much, how much it should turn. So signal is connected to GPIO 5. Now the reason why we're using a servo motor and not a regular motor is because we only want it to turn a certain angle. We don't want it to turn all the way around like other motors. Oh yeah, and by the way, this is a tower servo motor. That's why we're only applying the 5 volt pin to the Raspberry Pi and the power supply here. Otherwise, you probably wouldn't do that. Anyway, so yeah, that's the diagram. Oh, and one more thing. These are the pins and which tell whether they are output pins or input pins. So as you can see, GPIO 25, 19, 16, 23, 26, 20, 22, and GPIO 5 are all output pins. There's one input pin which is actually GPIO 7. And I'm actually going to tell you the numbers for the rest of the pins. Now VCC and ground we've covered. Now I'm only going to tell you echo. So basically the echo pin is connected to GPIO 7. So yeah, that's all done for the diagram and how I explain the wiring. I've connected my Raspberry Pi to its power supply, so now we're actually going to connect to it remotely with remote desktop connection. So here's how we're actually going to connect to it. I'm going to open the remote desktop connection app. If you don't have it, then you should download it. It's one way for you to connect your Raspberry Pi virtually. So you need to type in your IP address and then press connect. After that, it'll say configuring remote session and all. Then you'll see this window. And after you've full screened it, then type in your username and password. Um, Once you're done, press OK. Then wait a few seconds and you'll be in here. There we go. So I'm actually using Raspberry Pi's inbuilt Python IDE. It's called Honey. So once we open that, let's wait for this is actually the full file I saved it in. It's called autocard.py. So now I'm going to explain you how the code works and why we need that part. So first, in order to communicate with the Raspberry Pi's GPIO pins, we're importing rpi.gpio. That's just a library for communication of GPIO pins. Then we need to import time. Um, the time library basically has two things we need. One is time.time and one is time.sleep. I'll talk with that once we go further in the code. Then we're importing from a library called GPIO0. We're importing servo. That's just because we're using a servo motor. So then over here, we're just setting warnings false because otherwise it gives a bunch of warnings when you use the library. And then we're putting set mode as BCM mode. BCM mode is just one of the two modes. You can either put board or BCM. So then, as you can see over here, the command says motor A pin declaration and setup. So basically motor 1 is motor A and motor 2 is motor B. Now remember, it's always good to add comments, so if you need to change anything in the code, it'll be way easier to do that instead of scouting. So this is just the pin setups we've done. We've put variables of what pins we're using, and then we're just doing GPIO.setup to make them output pins, and this is actually the PWM. So it sends a PWM signal. Over here is the motor B pin declaration. It's basically the same thing but with different pin numbers and different names. Now we are at the sensor pin declaration and setup. So this is echo, which for those who know, according to the diagram, is going to be the input pin, and this is trigger, which is going to be the output pin. So, but for the sensor, it's in a different point of view, though. It's just the opposite. Now, this is the echo setup. So echo needs to be as a input pin, and trigger needs to be an output pin. So now let's scroll down. So down below are the functions we're going to be using to move our vehicles. Our vehicle. So over here you can see ENA and ENB. Those are basically going to be the enable pins connected to the motor driver to start the Lego NXT motors. Then over here, this set of things, iron 1 and iron 2 is for motor A, while iron 3 and iron 4 is for motor B. So basically, if we make iron 1 high and iron 2 low, it'll move forward. But if we do the opposite, it'll move backward. Same with iron 3 and iron 4, except that this time iron 3 has to be high and iron 4 needs to be low, or vice versa if you want it opposite. And as you can see over here, we did the exact opposite in a reverse function. Then we have our left function. So basically what we want to do for left is we want to move motor A forward and motor B backward. That's only because I'm using like the threads for it. Then over here we have U-turn. So when we move, so basically there's going to be something where if there's an obstacle in all direction, it should turn like completely 180 degrees. Then we have stop M. This is to stop all the motors. So over here, EN A and EN B will be set to 0, so it does nothing. Then all of the input pins will be set to low. And then we put a slight delay, which is time.sleep. I added a parameter here, as you can see in the function. So basically any number we type, it'll sleep for that amount of time. So now this is our measure function to measure the distance from how long it is from the sensor to an object. So basically we're making the trigger pin high or 1, then we sleep for about 10 microseconds, and then we make trigger low. This is so that it actually sends waves, but it won't always keep on sending waves. So anyways, then for as long as echo is 0 or when it starts high, no changes there, it should just keep on doing, it should do nothing. It just keep on checking there. That's why we put pass. But when it senses it's high, the condition over here is going to be false. So the while loop will no longer execute and go to start time. Time basically tells what the current time is as a floating point number in seconds. So then we basically do the same thing in this while loop except for as long as it's high. Then we put another variable stop time. That will record the time of when it received the signal. Then we actually start doing some calculation. We do d, which is actually a distance variable, equal to stop minus start times 17,000 to get our answer in centimeters. Stop minus start is actually in parentheses because the subtraction needs to be first. So once you do that, once stop minus start is done, it needs to be multiplied. Anyways, we will return d. This basically means we will just return the variable d. Anyways, now over here are these variables. This is servo center and servo right and servo left. They're all just abbreviated. Then we have a try here. You'll see why later in the code. Now we put a while true loop here. So basically we make it servo.max. So this basically tells it to move left. Then we put a slight delay, like about 0.5 seconds. And then we make it servo left equal to 0, just in case it's 1. Okay, all the servo things like servo center, servo right, and servo left are only going to be either 0 or 1. Then we put distance equal to measure. Here we're calling the measure function. So this will set distance to d in there because you can retrieve d. It's only in that function. Then we're putting an if statement here to check if dist is less than equal to 20.0 centimeters. This is because it'll probably return a number in a float. Then we put s left to 1. That means there's an obstacle there. We basically do the same thing down below, except this time it's dot mid here for straight, and it's s center for this part, and over here it's servo.min. This makes it right, and we're using the s right variable instead. Now we're going to convert those all into strings. So basically we're using the string function to convert them from integers to string. So we can actually add them in like side by side, not by numerical value like 3 or 2 or 1. So we need 3 of these because we need to convert all of them. And then we actually made a variable called join. So basically it'll add all of these once they're converted into strings. Then we have the ifs and elif statement to check where the obstacles are. So on this the left side means when the servo motor is on means when like the servo motor is turned left. The middle is like when the servo motor is turned straight, and the right is when the servo motor is turned right. So, for example, let's say 101. This means there's an object on the left or on the right. So basically, all the zeros stand for is nothing is there. So if there's nothing in the path or there's something on the left and right, then it should go forward. Oh, and by the way, there's 7 possible combinations with this. Also, you need to use an OR function, and I recommend it. It saves a lot of code. So basically, similarly, over here, if there's like a 001 or an object on the right or 011 object right or straight, then it's a turn left. So instead of going straight, it'll turn left. All this code, the only reason this code is here is just to make it go reverse and then turn left. Same thing over here, except this time it's right, and the numbers are moved by 1 space on the left. Let me move down. Then we have 1111. This doesn't have an OR statement because this means there's an object in all directions. So when it detects that, it should reverse, and this time it should U-turn, but there's a time dot sleep for 3.5 seconds. Now, now I'm explaining why I use try later. So when basically let's say something got wrong or it got stuck, then basically if keyboard interrupt is like activated, then it'll stop the code try is under in. And so first we need to stop M or stop the motors, and then it'll clean up all the GPIOs. So yeah, that's the code. So now I'm going to turn on my camera to show you how the vehicle will run.